first step in the audit process is typically reading the specification and documentation. For projects that have a specification of the design and architecture of their smart contracts, this is indeed the recommended starting point. However, very few new projects have a specification, at least at the audit stage. Some of them have documentation in parts. And to recall some of the key aspects of specification and documentation and the differences between the two. Specification starts with the project's technical and business goals and requirements. It describes how the project's design and architecture help achieve those goals. And the actual implementation of the smart contracts is really a functional manifestation of these goals, requirements, specification, design, and architecture. And understanding all these is critical in evaluating if the implementation indeed meets the goals and requirements. Documentation, on the other hand, is a description of what has been implemented based on the design and architectural requirements. So while specification answers the why aspect of something needs to be designed, architected, implemented the way it's been done, documentation, on the other hand, answers the how aspect. If something has been designed, architected, implemented without necessarily addressing the why aspect and leaves it up to the auditors to speculate on the reasons. And documentation, recall, is typically in the form of README files describing individual contract functionality combined with some functional NAT spec and individual comments within the code itself. Encouraging projects to provide a detailed specification and documentation saves a lot of time and effort for the auditors in understanding the project's goal structure and prevents them from making the same assumptions as the implementation, which is perhaps a leading cause of vulnerabilities. So in the absence of both specification and documentation, auditors are forced to infer those aspects such as the goals, requirements, design and architecture from reading the code itself and using tools such as Surya or the Slither printers that we discussed earlier. Identifying the key assets, actors and actions in the application logic from the code base that is required for understanding the trust and threat models is a complex and involved task. All this takes up a lot of time without the presence of a detailed and accurate specification, leaving very less time for the auditors to perform deeper and more complex security analysis. Auditors typically also use some fast tools such as linters or static analyzers that perform their analysis and finish running within seconds. Automated tools such as these, as we discussed, help investigate common security pitfalls at the Solidity or EVM levels and detect missing smart contract best practices. Such tools implement control flow and data flow analysis on smart contracts in the context of their detectors, which encode such common pitfalls and best practices. Evaluating their findings, which are usually available within seconds or few minutes, is a good starting point to detect common vulnerabilities based on well-known constraints or properties of Solidity language, EVM, or the Ethereum blockchain itself. False positives are possible among some of the detector findings, which need to be verified manually to check if they are true or false positives. And these tools can also miss certain findings, leading to false negatives. Best examples of static analyzers in this space are Slither and Maru, both of which we have touched upon in the earlier slides of this module. Manual analysis is perhaps the most critical aspect of smart contract audits today. Manual code review, as we have discussed, is required to understand business logic and detect vulnerabilities in it. Automated analyzers cannot understand application level logic and infer their constraints. and so are limited to constraints and properties of the Solidity language EVM or the Ethereum blockchain itself. Manual analysis of the code is therefore required to detect security relevant deviations in the implementation from those captured in the specification or documentation. And as we have discussed, in the absence of specification or documentation, auditors will be forced to infer business logic and their implied constraints directly from the code itself or from discussions with the project team, and only thereafter evaluate if those constraints or properties hold in all parts of the code base. We'll take a deeper look at different approaches to manual analysis in the last part of this module. In contrast to the fast tools that we discussed earlier, there are also what may be thought of as slow or deeper tools. These are tools in categories of fuzzing, symbolic checking, or formal verification. Running such deeper automated tools, fuzzers such as Echidna, symbolic checkers such as Manticore, Mithril, tool suite such as Mythex, or formally verifying custom properties with Scribble or Sotora Prover takes more understanding and preparation time to formulate such custom properties, but helps run deeper analysis which may take minutes to run, but helps discover edge cases in application level properties and mathematical errors, among other things. Given that doing so requires understanding of the project's application logic, such tools are recommended to be used at least after an initial manual code review, or sometimes after deeper discussions about the specification implementation with the project team itself. Also, analyzing the output of these tools requires significant expertise with the tools themselves, their domain-specific language, and sometimes even their inner workings to interpret their findings. Evaluating false positives is sometimes challenging with these tools, but the true positives they discover are typically significant and extreme corner cases missed even by the best manual analysis. Brainstorming with other auditors is often helpful. Given enough eyeballs, all bugs are shallow is a premise that is referred to as Linus's law, and this might apply with auditors too if they brainstorm on the smart contract implementation, assumptions, findings, and vulnerabilities. While some audit firms encourage active or passive discussion, there may be others whose approach is to let auditors separately perform the assessment to encourage independent thinking instead of group thinking. The premise is that group thinking might bias the audit team to focus only on certain aspects and not others, which may lead to missing detection of some vulnerabilities and therefore affects the effectiveness. A hybrid approach may be interesting, where the audit team initially brainstorms to discuss the project goals, specification, documentation, and implementation, but later firewall themselves to independently pursue the assessments and finally come together to compile their findings. Finding a balance between the overhead of such an approach and the benefits of such an overlap in effort may be an interesting consideration. Discussion with the project team is another critical part of the audit process. Having an open communication channel with the project team is useful to understand their scope, trust, threat models, any specific concerns, to clarify any assumptions in specification, documentation, implementation, or to discuss interim findings. Findings may also be shared with the project team immediately on a private repository to discuss impact, fixes, and other implications without waiting to discuss it at the end of the audit period. If the audit spans multiple weeks, it may also help to have a weekly sync-up call for such discussions and updating the status. A counter point to this is to independently perform the entire assessment so as to not get biased by the project team's inputs and opinions, which may steer the auditors in certain directions, potentially without letting them pay attention to other aspects. An audit report is a tangible deliverable at the end of an audit, and therefore report writing becomes a very critical aspect of the entire audit process. The audit report is a final compilation of the entire assessment and presents all aspects of the audit, including the audit scope, coverage, timeline, team effort, summaries, tools, techniques, findings, exploit scenarios, suggested fixes, short-term, long-term recommendations, and any appendices with further details on tools and rationale. An executive summary typically gives an overview of the audit report with highlights, lowlights, illustrating the number, type, severity of vulnerabilities found, and an overall assessment of risk. It may also include a description of the smart contracts, actors, assets, roles, permissions, access control, interactions, threat model, and existing risk mitigation measures. The bulk of the report focuses on the findings from the audit, their type, category, likelihood, impact, severity, justifications for these ratings, potential exploit scenarios, affected parts of smart contracts, and potential remediations. It may also address subjective aspects of code quality, readability, auditability, and other software engineering best practices related to the documentation, code structure, function variable naming conventions, test coverage, etc. that do not immediately pose a security risk but are indicators of anti-patterns and processes influencing the introduction and persistence of security vulnerabilities. The audit report should be articulate in terms of all these information and also actionable for the project team to address all raised concerns. The delivery of the audit report is another important aspect in the audit process, and perhaps the final milestone when such a report is published and presented to the project team. Unless interim findings or status is shared, this will be the first time the project team will have access to the assessment details. The delivery typically happens via a shared online document and is accompanied with a readout where the auditors present the report highlights to the project team for any discussion on the findings and their severity ratings. The project team typically takes some time to review the audit report and respond back with any counterpoints on findings, severities, or suggested fixes. Depending on the prior agreement, the project team and the audit firm might release the audit report publicly after all required fixes have been made, or the project may decide to keep it private for some reason. Evaluating fixes is typically the final stage in the audit process and a very critical stage. After the findings are reported to the project team, they typically work on any required fixes and then request the audit firm for reviewing such fixes. Fixes may be applied for a majority of the findings, and the review may need to confirm that applied fixes, which in some cases could be different from what was recommended, that these fixes indeed mitigate the risk reported by the findings. Some findings may also be contested as not being relevant, outside the project's threat model, or simply acknowledged as being within the project's acceptable risk model. Audit firms may evaluate the specific fixes applied and confirm or deny their risk mitigation. And unless it is a fix or retainer type of audit, this phase typically takes not more than a day or two, because it would usually be outside the agreed upon duration of the audit. But most audit firms generally accommodate this to help ensure the security of the project. So these are the 10 steps of an audit process that you can expect to see within an audit or an audit firm. Like mentioned earlier, these are generalized opinions, and the specifics of these different steps, their order, the level of effort that is put in each step, and the philosophies behind them will surely differ across different audit firms. But nevertheless, this is something that's very critical that needs to be paid attention to and understood to appreciate the different steps of the audit process. In the final part of this module, let's dive deeper into the many approaches to manual review. As we mentioned a couple of times, the manual review step is perhaps the most critical component of smart contract audits today. So auditors have different approaches to manually reviewing smart contracts for vulnerabilities. They may be along the lines of starting with access control, starting with asset flow or control flow, data flow, inferring constraints, understanding dependencies, evaluating assumptions, and evaluating security checklists. Auditors may start with one of these as their preferred approaches and then combine multiple of them for best results. These are very subjective aspects, but we will explore them in some detail to understand what they may entail. Starting with access control is very helpful because access control, as we have discussed, is the most fundamental security primitive. It addresses who has authorized access to what, or which actors have access to what assets. While the overall philosophy might be that smart contracts are permissionless, in reality, they do indeed have different permissions or roles for different actors who interact or use them, at least during their initial guarded launch. The general classification is that of users and admins, and sometimes even a role-based access control. Privileged roles typically have control over critical configuration and application parameters, including emergency transfers, withdrawals of contract funds. And such access control is typically enforced in modifiers, as we have discussed in the earlier modules. And also more generally, we are the visibility of functions such as public, external versus internal or private, which we also discussed in the context of solidity. Therefore, starting with understanding the access control implemented by smart contracts and checking if they've been applied correctly, completely, and consistently is a good approach to detecting violations which could be critical vulnerabilities. One can also start with the asset flow. Assets are Ether or ERC20, ERC721 or other tokens managed by smart contracts. Given that exploits target assets of value, it makes sense to start evaluating the flow of assets into, outside, within, and across smart contracts and their dependencies. The questions of who, when, which, why, where, what, type, and how much are the ones to be asked. For who, assets should be withdrawn, deposited only by authorized specified addresses as per application logic. For when, assets should be withdrawn, deposited only in authorized specified time windows or under authorized specified conditions as per application logic. for which assets only those authorized specified types should be withdrawn deposited. For Y, assets should be withdrawn deposited only for authorized specified reasons as per application logic. For where, assets should be withdrawn deposited only to authorized specified addresses as per the logic. For what type, assets only of authorized specified types should be withdrawn deposited as per the logic. And finally, for how much, assets only in authorized specified amounts should be allowed to be withdrawn deposited, again as per the application logic. So these are all the various aspects of asset flow that need to be evaluated. Evaluating control flow is a fundamental program analysis approach. Control flow analyzes the transfer of control, that is the execution order, across and within smart contracts. Inter-procedural control flow, where procedure is just another name for a function, is typically indicated by a call graph which shows which functions or callers call which other functions or callees across or within smart contracts. Intra-procedural control flow that's within a function is dictated by conditionals, the if-else constructs, loops for while, do, continue, break constructs, and return statements. Both intra and inter-procedural control flow analysis help track the flow of execution and data in smart contracts. And therefore, as you can imagine, is a fundamental program analysis approach to evaluate security aspects. Evaluating data flow is another fundamental aspect of program analysis, which analyzes the transfer of data across and within smart contracts. Interprocedural data flow is evaluated by analyzing the data, that's the variables and constants, used as argument values for function parameters at call sites and their corresponding return values. Intra-procedural data flow, on the other hand, is evaluated by analyzing the assignment and use of variables or constants stored in storage, memory, stack, call data locations along the control flow paths within functions. Both intra and inter-procedural data flow analysis help track the flow of global or local storage memory changes in smart contracts. And given that data flows where control flows, they work together to help with program analysis of smart contracts in helping detect security vulnerabilities. Inferring constraints is an approach that is almost always required. Program constraints are basically rules that should be followed by the program. Solidity level and EVM level security constraints are well known because they are part of the language and EVM specification. However, application level constraints are rules that are implicit to the business logic implemented and may not be explicitly described in the specification. Example of such a constraint may be to mint an ERC721 token to an address when it makes a certain deposit of ERC20 tokens to the smart contract and burn it when it withdraws the earlier deposit. Such business logic specific application level constraints may have to be inferred by auditors while manually analyzing the smart contract code. Another approach to inferring program constraints without having to understand the application logic is to evaluate what is being done on most program paths related to a particular logic and treat that as a constraint. And if such a constraint is missing on one or few program paths, then that could be an indicator of a vulnerability, assuming that the constraint is security related, or those could simply mean that Such program paths are exceptional conditions where the constraints do not need to hold. Understanding dependencies is another critical approach to manual analysis. Dependencies exist when the correct compilation or functioning of program code relies on code or data from other smart contracts that were not necessarily developed by the project team. Explicit program dependencies are captured in the import statements and the inheritance hierarchy. For example, many projects use the community developed, audited and time-tested libraries from OpenZeppelin for tokens, access control, proxy, security, etc. Composability in Web3, as we have discussed, is expected and even encouraged via smart contracts interfacing with other protocols and vice versa, which results in emergent or implicit dependencies on the state logic of external smart contracts via oracles, for example. This is especially of interest or concern for DeFi protocols that rely on other related protocols for stable coins, yield generation, borrowing, lending, derivatives, oracles, etc. Assumptions on the functionality and correctness of such dependencies need to be reviewed for potential security impacts. A meta-level approach is that of evaluating assumptions. Many security vulnerabilities result from faulty assumptions, such as who can access what and when, under what conditions, for what reasons, etc. Identifying the assumptions made by the program code and verifying if they are indeed correct can be the source of many audit findings. Some common examples of faulty assumptions are only admins can call these functions. Initialization functions will only be called once by the contract deployer, which is relevant for upgradable contracts. Functions will always be called in a certain order as expected by the specification. Parameters can only have non-zero values or values within a certain threshold. For example, addresses will never be zero value. Certain addresses or data values can never be attacker controlled. They can never reach program locations where they can be misused. In program analysis literature, this is known as taint analysis. Or function calls will always be successful, and so checking for return values is not required. And the eighth and final approach to manual analysis is the one we are using in this bootcamp, which is that of evaluating security checklists. Checklists are lists of itemized points that can be quickly and methodically followed, and even referenced later by their list number, to make sure all listed items have been processed according to the domain of relevance. For some context, for those who aren't aware of the significance of checklists, this checklist-based approach was made popular in the book The Checklist Manifesto, How to Get Things Right by Atul Gawande, who is a noted surgeon, writer and public health leader. And this idea is best summarized in the review of his book by Malcolm Gladwell, who writes that Gawande begins by making a distinction between errors of ignorance, mistakes we make because we don't know enough, and errors of ineptitude, mistakes we make because we don't make proper use of what we know. Failure in the modern world, he writes, is really about the second of these errors, and he walks us through a series of examples from medicine showing how the routine tasks of surgeons have now become so incredibly complicated that mistakes of one kind or another are virtually inevitable. It's just too easy for an otherwise competent doctor to miss a step or forget to ask a key question, or in the stress and pressure of the moment to fail to plan properly for every eventuality. Gawande then visits with pilots and the people who build skyscrapers and comes back with a solution. Experts need checklists, literally written guides that walk them through the key steps in any complex procedure. In the last section of the book, Gawande shows how his research team has taken this idea, developed a safe surgery checklist, and applied it around the world with staggering success. So, this glorifying review should hopefully motivate a better appreciation for checklists. To apply this to our context, consider the mind-boggling complexities of the fast-evolving Ethereum infrastructure, new platforms, new languages, new tools, new protocols, and the risks associated with deploying smart contracts managing millions of dollars. There are so many things to get right with smart contracts that it is easy to miss a few checks, make incorrect assumptions, or fail to consider potential situations. Checklists are known to increase retention and have a faster recall. The hypothesis, therefore, is that smart contract security experts need checklists too. Smart contract security checklists, such as the two security modules we have discussed earlier in this bootcamp, will help in navigating the vast number of key aspects to be remembered, recalled, and applied with respect to the pitfalls and best practices. They will help in going over the itemized features, concepts, pitfalls, best practices, and examples in a methodical manner without missing any items. They will also help in referencing specific items of interest. So, for example, number 42 in Security Pitfalls and Best Practices 101, or number 98, which is this slide, in Audit Techniques and Tools 101. Presenting proof of concept exploit scenarios could be a part of certain audits. Recall that exploits are incidents where vulnerabilities are triggered by malicious actors to misuse smart contracts, resulting, for example, in stolen or frozen assets. Presenting proof of concept of such exploits, either in code or written descriptions of hypothetical scenarios, make audit findings more realistic and relatable by illustrating specific exploit paths and justifying the severity of findings. It goes without saying that codified exploit should always be on a testnet, kept private, and responsibly disclosed to project teams without any risk of being actually executed on live systems, resulting in real loss of funds or access. Descriptive exploit scenarios should make realistic assumptions on roles, powers of actors, practical reasons for their actions, and sequencing of events that trigger vulnerabilities and illustrate the paths to exploitation. We have talked about estimating likelihood, impact, and severity of the findings. Likelihood indicates the probability of a vulnerability being discovered by malicious actors and triggered to successfully exploit the underlying weakness. Impact indicates the magnitude of implications on the technical and business aspects on the system if the vulnerability were to be exploited. Severity, as per OWASP, is a combination of likelihood and impact. With reasonable evaluations of those two, severity estimates from the OWASP matrix should be straightforward. However, estimating if likelihood or impact are low, medium, or high is non-trivial in many cases. If the exploit can be triggered by a few transactions manually without requiring much resources or access, example not being an admin, and without assuming many conditions to hold true, then the likelihood is evaluated as high. Exploits that require deep knowledge of the system workings, privileged roles, large resources, or multiple edge conditions to hold true are evaluated as medium likelihood. Others that require even harder assumptions to hold true, such as minor collusion, chain forks, or insider collusion, for example, are considered as low likelihood. If there is any loss or locking up of funds, then the impact is evaluated as high. Exploits that do not affect funds but disrupt the normal functioning of the system are typically evaluated as medium, and anything else is of low impact. Some evaluations of likelihood and impact are contentious and debated sometimes between the audit and project teams, and sometimes even the security community at large. And this typically happens with security conscious audit teams pressing for higher likelihood and impact, while the project teams downplay the risks. So, finally, to summarize, audits are a time, resource, and expertise bounded effort where trained experts evaluate smart contracts using a combination of automated and manual techniques to find as many vulnerabilities as possible, whose difficulty, impact, and severity levels might vary. Similar to what Dijkstra once said about software testing, audits can only show the presence of vulnerabilities but not their absence. So with that, we have come to the end of this module on Audit Techniques and Tools 101, where we have touched upon 101 key concepts related to the various aspects of auditing as related to the tools and techniques used. So hopefully you have a much better understanding and appreciation for what it takes to do smart contract security audits now. And like always, I would again encourage you to look at the related references, especially the various tools, to get a practical feel for their capabilities and challenges.